Okay, so as promised, some more factoring of polynomials. First step is to look for greatest common factor of all three terms, or all the terms. In this case, we only have three. There we've got 3 and 3 and x and x. 3 goes in here, x goes in here. No x, and 3 is not a factor of 25. So these have 5 as a common factor. This doesn't have 5 as a common factor. No GCF. So I move on to my next goal, which is to look for a special polynomial. And it's looking good. 9's a perfect square, so 9x squared. That's 3x. 25, that's a perfect square. So I could say 5 times 5 is 25. It's plus here, that's good. This is also positive, so I've got all positives. That could be it. But here I've got 9x squared and 25. Those can't both be equal to 3x plus 5 squared. Right? So how do we know which one is? Or even if either of them are. Maybe neither of these, in fact, are perfect square trinomials. To check a perfect square trinomial, it's not enough to have a perfect square for your first and last terms. That middle term also has to check out. Right? Our formula, a plus b squared, a squared, and b squared, but also the a times b and the b times a, if we're distributing there. A times b, b times a, that's 2ab. So this middle term has to be twice this product. So 3 times 5 is 15, so that's 15x. Double 15x, we get 30x. This is a perfect square trinomial. We're all set. 78x is not equal to double 3x times 5, so this is not equal to 3x plus 5 squared. But that doesn't mean it can't be factored. What it means is we can potentially factor it in some other way. We have to try, right? For all of these, the only way to know for sure if they can or cannot be factored is to try to factor them. Same thing with large numbers. How do you know if a large number is a prime number? You try to factor it, and then if none of the potential factors goes in evenly, then you know it's prime. We have to try to factor this. So, come on, it's too fat. 9x squared, to get 9x, well, to get x squared, we know it's going to be x and x. And to get 9, it could be 3 and 3, or it could be 9 times 1. To get 25, that could be 5 and 5. Now, I'm not going to write that in here, because if this is 5, that's going to be 5. We already rejected that option. We already rejected 3x plus 5 squared. So instead of putting those 5's in, the only other choice to get 25 is 1 and 25. So I'm going to try that. And if that doesn't work, then I'll try the 9x and x, and then that could be 1 and 25, or it could be, I didn't give myself enough room here. Ignore this for now. Or it could be 25 and 1, or it could be 5 and 5. Now I don't have to check 3x plus 25 and 3x plus 1 because these first two are really the same, just the commutative property has them switched, right? 3x plus 1, 3x plus 1. 3x plus 25, 3x plus 25. It's the same two factors, just reversed order. Right? So I'm not going to do that. I'm not going to write that in and squeeze out my work here. Right? Down here, 9x plus 1 is not the same as x plus 1. Right? Because this first term is not the same as this first term, 9x is not the same as 1, these two will give me different outcomes when I multiply them out. So let's check these. 3 times 3 is 9, x times x is 9x squared, 9x squared, 9x squared, 9x squared. Of course, that's where these guesses came from. I wanted to guess coefficients here, I guess the entire term here, so that it would multiply out to my first term. Check the last one. 1 times 25 is 25. 1 times 25 is 25. 25 times 1 is 25. 5 times 5 is 25. All of those positive. What I really need to check is my outer inner. Right? 3x times 25, 3 times 25 is 75. 1 times 3 is 3 with the x. 75x plus 3x, those are like terms. That's 78x. That's what I want. I'm done. If your first guess works, great. Don't bother with any of this. You already know the answer. Why would you guess again if you already guessed correctly? But for the sake of teaching, let's say this wasn't our first guess. Let's go through the rest of these. So 9 times 25, that's a big number. 1 times x is just 1x. So I know I'm going to get plus 1x. 10 times 25 is 250. I can do that in my head. Right? So it's a little bit less than 250. That's nowhere close to 78. Right? I don't actually need to calculate 225 precisely. 9 times 25 is 225. Because I know this sum is not going to be in the right ballpark to get 78. I can reject that. Move on to the next one. 9 times 1 is 9x. 25. 9 and 25. 25, 35. No, 34. Okay, it's about half. Right? 68 would be double. Doesn't matter if it's half or whatever it is, we know it's too small. That's not going to work. Right, try here. 9 times 5 is 45. 5 times x is 50x. Oh, so 5 times x is 5x. And 45 plus 5 is 50x. Got ahead of myself here. So if I had 9x squared plus 50x plus 25, I have discovered that that's equal to the factored 9x plus 5 times x plus 5. I could have done that for these two, right? But that's not the polynomial I was given, so this is not my answer. This is the polynomial I was given. This product of these two binomials is equivalent to that. The multiplication gives me this answer, so this is the factored form. This one, let me switch colors here. This is simplified. And this is factored. Oh, that handwriting is awful. Let's try again here. And this one is the factored form. It asked me to factor. It's asking for the factored form of the polynomial. Now let's open up a new page to look at this next one. Okay, so now we're factoring x squared plus 9x plus 14. Backing off a little bit to slightly easier problem here. Why is it easier? Because we have that magical leading coefficient of 1. The only way to factor x squared is x times x. If I try doing something like x squared times 1, let's say 14, just pick anything, let's say 7 and 2. X squared times, wait a minute, 1 plus 2 is 3. That's not going to give me a trinomial with an x term. That's going to give me 3x squared plus 21. Okay? The only way for these two terms not to be like terms is if one of them has an x and one of them is a constant term. Okay? That is not going to work. To get x squared here, it's going to be x and x. It's going to be x and x. Right? 9x squared, that's going to be maybe 3x and 3x, or maybe 9x and 1x. We don't know yet. Right? But for here, x squared is x and x. So 14 could be 1 and 14. Rarely will they give you problems that are 1 times the other number. Sometimes, I think that's what we had back here. Right? 25 was 1 and 25. But that's not usually going to be our first guess. 14 is 7 times 2. To get a positive 9, I need a positive 7 and a positive 2. Right? Let's double check. X times x is x squared. X times 2 is 2x. 7 times x is 7x. 7 times 2 is 14. 2 plus 7 is 9x. That is correct. Now this next one's a little bit different here. Instead of a minus 14, instead of a plus 14, it's a minus 14. So when I'm factoring that, I can't just have 7 and 2. It's got to be negative 7 and positive 2, or positive 7 and negative 2, or 14 and 1, right? Well, to get 9x in the middle here, 2x minus 7x I'm not getting a sum of 9 anymore. I'm getting 2 plus negative 7. I'm getting negative 5. Or if I flip it around, x squared plus negative 2x plus 7x. All right, that's giving me positive here. That's good. 7's bigger than 2. 7 minus 2, though, that's 5x for a middle term, not 9x. I could try 1 and 14. That's not going to give me a positive 9. It's not going to work out. This is a prime polynomial. So we either just write it out there, cannot be factored, or we say x squared plus 9x minus 14 is a prime polynomial. Right? Depending on the phrasing of the question, one of those two will be your response. Right? In fact, most polynomials cannot be factored. If we think of regular whole numbers, most whole numbers are not prime. There are a lot more composite numbers than there are prime numbers. But a lot more has to line up for a polynomial to be factorable. Most polynomials are not factorable. But for the ones that are factorable, we want to give you a lot of practice in factoring them. So most of your homework will be given polynomials that can be factored. You just have to watch out for, if you try every possibility and it doesn't work, you're done. Okay? So here we have an x squared. We have a minus 14. There's no middle term here. So if I were to use FOIL, those two terms have to add up to something. The only way they add up to 0 is if I'd have 7x and a negative 7x, or 2x and a negative 2x. The only way for that x term to not be there is if this were a difference of squares. So let's actually switch colors so that we're not running into our other problems here. So equals x plus something, x minus something. Well, 14 is not a perfect square. So if I'm limiting myself to integers, this isn't going to work. Right? Now, what you'll see next semester is you can kind of cheat. And you can say, well, the square root of 14 times the square root of 14 is 14. But that's cheating. We're not dealing with non-rational, with irrational coefficients here. So we'll just say again, cannot be factored. Right. If we move on to the next problem, you notice 9x squared, even though we brought a 9 back in, 9's a perfect square, 25 is also a perfect square, no middle term. One of them's positive, the other's negative. Doesn't matter which one you have for which here. This is the classic difference of squares. You want to recognize that. And then here I've got x squared of 13 and a 14. Well, 7 plus 2 is 9. But I'm not doing plus because this is negative. I need two different signs. Right? Not 9x squared anymore, so I have the nice, easy, plain x squared. To get 14 as negative, one's got to be negative, the other positive. Well, 13 is 1 less than 14, so it's got to be 14 and 1. X squared plus x minus 14x minus 14. X minus 14x, 1 minus 14, negative 13. Oh, I want positive 13. So I just flip the sign. Right? To get that 14 is positive and the 1 is negative, I have to flip the sign. So this is equal to x plus 14, x plus negative 1, in other words, x minus 1. With more and more and more and more practice, this process of guessing what factors might work here and then seeing which ones will actually work for all three terms, that process gets pretty fast. But it requires practice, right? Learning how to ride a bike, you just have to go for it. There's no real good advice to know exactly how to steady yourself on your handlebars and get your weight distributed right on your hips and everything. You just have to get that weight the right way, get your initial force on the pedal and that momentum going with the pedals the right way through a lot of trial and error and a lot of practice. And once you've got it, you're good. It's easy. Once you've got this process, some problems are harder than others, but it gets easier and easier as you recognize patterns and go through the process. Right? Your process will always be the same. Looking for a GCF that you can factor out, then look for whether it fits the format of one of the special polynomials. And then if that doesn't work, we'll try to use reverse FOIL. Now, there are some other methods here besides guess and check. They do work. They don't require as much practice and experience to get to be good at them. But the learning curve never gets easier, right? If you think about competence over time, the guess and check is really hard at first, but then it gets easier. The other methods start out not so hard, but they always take a long time. That doesn't quite work here, right? Not quite as hard at first, maybe getting a little bit easier, but they're definitely plateaued here, right? Practicing this method will pay its dividends in the long run. And once you start dealing with problems like this next semester, you definitely need to get fast at factoring even more complex polynomials. The way to get fast is to use this quickly with the with the backing up experience of recognizing the patterns.